Happy Monday, everyone. Hope that you're having a great Monday. I'm sorry that I'm not here today. I have taken a day off. Everything is fine. And I will be back tomorrow. Just some things that I had to do and couldn't get them done this weekend. And that means they have to get done today. So, anyways, I'm kind of upset because I enjoy theoretical probability. And probability and statistics is probably one of my favorite units to teach. But I still have a few lessons to do with you. So let me just give you a quick reminder of what this week's going to look like. We've got 3 probability lessons. So Monday, Tuesday, Wednesday, probability, probability, probability. Then we're going to take a little quiz on Thursday. And then, of course, Friday will be your last Friday without having to come to school for a while for the rest of the year. So, anyways, but that's only like 6 more weeks. So you guys got this. And then we get a fall break, and we'll jump back into statistics when we come back. But anyways, let me go ahead and go through this with you. Miss Higdon is your sub today, and she's great. If you have any questions, she can absolutely help you, and she is good at helping. So if you need her to pause the video, by all means, ask her, and she will do that. If you need her to explain something, again, ask her, and I promise you, she can do it. So, anyways, let's go ahead and start talking about theoretical probability. So, probability is the measure of how likely an event is to occur. And you deal with this kind of stuff all the time, with so many different aspects of your life. So this is going to be something that I think one of the reasons why I like it so much is it's so easy to actually apply. When we start talking about factoring polynomials, that's hard to apply, right, in your life. But when it comes to probability, you guys are going to think like this a lot moving forward. So anyways, the set of all possible outcomes is going to be called a sample space. And for equally likely outcomes, the theoretical probability of an event, probability of E, is the ratio, hopefully that kind of tell you what you're doing, of the number of favorable outcomes to the total number of outcomes. So again, right off the bat, understand what we're talking about here. A ratio, right? A ratio is a fraction, and that fraction is going to have the favorable outcomes on top over the total outcomes on the bottom. Okay? So, again, that's what we got. That's what we're going to be talking about today in our lesson. We're going to also talk about this thing from 2 perspectives. We're going to talk about simple versus compound events. Okay? So when we talk about simple events, we're talking about the probability of one event occurring, okay? One event. So, for example, if I look at number 1, it says a jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? So again, we're not talking about choosing a bunch of different, it's like you've got these marbles in a hat or a cup and you want to reach down in there. What's the chance that you would end up getting a red marble? Well, again, favorable over total. What are the favorable amount when it comes to getting a red marble? Well, there's 32 marbles, right, that are red. So 32 is the favorable. And then, of course, in the denominator, you have the total outcomes. How many total marbles are actually in the hat, if you will? Well, there's 32 red, 28 blue. So 32 plus 28 is 60. So the total number of outcomes, the total number of marbles that you could possibly grab out is 60. So my probability of grabbing a red marble is 32 out of 60. Now listen, with probability, if you can reduce, you got to reduce it. So 32 over 60 will reduce. My recommendation for you to do would be get real familiar with your alpha y equal key, because if it will reduce, it'll do it for me. Okay, so as we move up into bigger numbers, just throw it into alpha y equals number 1. And if it will reduce it, it will give you the simplified value. So the simplified value of this is 8 out of 15. You have an 8 out of 15 chance of pulling out a red marble. I hope that makes sense to you. Okay, so let's look at a couple more of these. Look at number 2. a letter in the word restoration is randomly selected. Okay, so it's like they're just all written or cut out into little pieces of paper. What's the probability of selecting a vowel? So this one you have to think a little bit more, okay? Because it's not like, oh, well, just if what's the chance of you pulling out or probability of pulling out an A? It's all vowels. So you got to just recognize all your vowels. You got E, you got O, A, I, O. So that's 1, 2, 3, 4, 5. Hopefully I didn't miss any. So when it comes to vowels, there are 5 that are possible, right? There are 5 that are favorable for actually being a vowel. And then, of course, what's the total number of outcomes in this case? Well, that's all the letters of the word restoration. So you just got to tally them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11. Now, feel free to throw that into alpha y equals. Most of you guys recognize that that cannot be reduced. So the probability of selecting a vowel is 5 out of 11. And that's how you do it, okay? So let's keep on moving. We'll just go down to the right. Number 4. 2 dice are rolled. What is the probability that the sum of the 2 dice on the next roll is at least 9? So the sum. Now this one's a little bit more challenging, okay? Because you got to know a couple things about a dice. 1, how many numbers are on a regular die? 6, right? So now all of a sudden you're like, well, you're adding these all up, right? So whatever the first dice is, you're adding it to the second dice. So here's what you got to understand. Here in the first dice, I have a chance of getting a 1, 2, 3, 4, 5, or a 6, right? But on the second dice, I have the same chances, a 1, 2, 3, 4, 5, or 6. So you're going to roll a combination of 2 of these, right? So how many have at least? Now, that means something too. What does at least mean? If it's at least 9, that means it's 9 at the least, right? That's the smallest it can be. So the sum of these two have to be at least 9. So it could be 9 or above. So I want you guys to understand something. If I were to say, hey, could I add something with the 1 here? See, if I did 1 plus 1, that's just 2. That's not 9 or higher. So there's no way that would give me a chance. Even if I went 1 plus 6, that's only 7, which is not at least 9. So 1 wouldn't actually be able to roll with anything. But what about 2? Yeah, well, 2 plus 6, your biggest number, that's still just 8. So that won't. So the next number is the first time that could even happen. 3 plus 6 is 9. But any other number, 3 plus 5 is not at least 9. 3 plus 4 is 9. So there's no other. Okay, but how about if I rolled a 4 on the first die? The next one could be a 5 or a 6, right? So how many different rolls is that? So far, how many red lines do I have? 1, 2, 3. I have 3 chances so far where if I added them up, it would be at least 9. Okay, so how about if my first dice was a 5? Well, I could roll it with 5 and 4. That's 9. 5 and 5, that's 10. And 5 and 6, that's 11. So those all 3 work. So now we're at what? 1, 2, 3, 4, 5, 6. And then, of course, 6 could roll with 3. It could roll with 4, 5, or 6. So that's 4 possibilities. So I know the red lines are kind of out of control at this point. But if you remember, I had 3 plus 3, 6 plus 4 is 10. There are 10 different possibilities where when I roll it, it's going to give me a sum of at least 10. I hope that makes sense to you. Now here's the other challenging part. Well, what are my total number of possible rows or rolls? Do I just go through here and just go 1, 1, 2, 3? No, every one can be done 6 different ways. So there's 6 times 6 ways. So 6 times 6 is 36. So my total number of possible rolls here is 36. So 10 out of the 36, you would roll at least a 9 or greater. And that's when you start thinking about gambling, okay? And again, I'm not condoning or talking about gambling, but I want you to definitely understand one thing. It's called gambling for a reason. Because when you start talking about the chances of something happening that are kind of far-fetched, with all the different possible rolls, what would be the chance of you rolling at least a 9? Well, 10 out of 36, or if you reduce that, that reduces down to 5 out of 18. That's not great chances, right? It's well under 50%. So again, that's what happens when you take a chance. You start dealing with things of that nature. So kind of tough, but I wanted you to at least see a problem that does that. Okay. All right. So let's keep on going. I want to look at one more over here because there's a couple things I want you to know about a deck of cards. If you don't know about a deck of cards, you need to for this unit. First, there are 4 different suits that we call them, and each suit has 13 cards in it. So that means there are a total of 52 cards in a deck. Okay? 52 total cards in all decks. Now, when you talk about a deck, you have 2 reds. They are diamonds and hearts. And then you have clubs and spades. And of these, they all have, again, 13 cards, okay? Now, if you're not 100% sure or aware of this, they start at 2, and they go to 3, 4, 5, 6, 7, 8, 9, 10. And then we have what we call face cards that are jack, queen, king, and then an ace. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's the cards that you would pull out of a deck. And of course, we have, like I said, diamonds and hearts. So, for example, number 5. Now that you know that, and you can come back to that at any time you'd like, what's the probability of drawing a heart or a club from a standard deck of cards? So again, my favorable outcomes are it could be a heart or a club. Well, how many hearts and how many clubs did I say there were? Well, there's 13 of each suit. So there's 13 hearts, there's 13 clubs. So your favorable outcomes would be 26. But then, of course, out of how many? What's the total number of cards in that deck? Well, we said that's 52. So that would be a 1 out of 2 chance, which wouldn't be too bad, I don't guess. But again, it's a chance that you would have to take. All right. So that is what we call theoretical probability. Theoretical probability. And that was what we call simple events. Just really basic. We could have done all these examples, but I want to get through some more of them in this class where you have a little bit of time to work at the end. So sometimes when you're dealing with problems like this, because of the nature of probability, it's sometimes better to do or find the complement of an event. Well, a complement of an event is the probability that the event will not occur, okay? That it won't happen. The complement of an event is the probability of the event not happening, okay? Sometimes it's easier to total up what won't work than it is to tally up what will work. Again, that's kind of sad, but that's true. So since the sum of all probabilities in a sample space is 1, then we can find the probability of an event not happening, which is called probability of not event. We can find that by doing 1 minus the probability that the event occurred. Okay? Now let me make sure you understand this whole concept of 1. Remember, this is a probability is all about ratios. It's fractions. And with fractions, you divide. It's a percent. So if I have perfect number of possibilities, that would be whatever the number on the top is, the same number as the bottom. 5 out of 5. 52 out of 52. 100% of it happening. That's why the sample space is 1. You're never going to have a probability of something happening better than 100%. Like 100% is as good as the chances can get. Okay, you can't get a better chance than 100%. There's no such thing as, oh, well, there's a 200% chance of it raining today. No, I mean, there's no way you can have 200%. It's 100%. It's going to rain. That's the highest you can go. That's probability. So that's why the sample space is 1. So if I want to find the probability of an event not occurring, I'm going to subtract the probability of that event occurring from 1. So look at number 7. Number 7 says the probability that it will snow tomorrow is 7 out of 20. And we're way past that chance, so don't get excited. That's not even true. What's the probability that it will not snow? Well, I think you guys can figure that out on your own, but I do want to remind you, for harder problems, the probability that it won't happen is 1 minus 7 over 20. Now, back in the day when you changed 1 to a fraction, you'd make that 20 over 20, and then you would subtract, and 20 minus 7 would give me 13 over 20. There's a 13 out of 20 chance that it won't snow. That is what we would call complements. When you subtract the probability that an event will occur in order to find the probability that an event will not occur. Okay, let's look at a couple more of these. Number 8. A month of the year is randomly selected. What is the probability of getting a month that does not begin with the letter A? All right, so just think about it. We already know the bottom number, right? The bottom number, of course, is 12. Why? Well, because, I mean, you're talking about months of the year. There's only 12 months in a year. That won't change. That's a constant, right? So what is the probability of a month that does not begin? Well, let's again subtract the chance that it is a month that starts with an A from 1. So how many start with A? Well, not January, February, March, April, May, June, July, August, September, October, November, December. That's it. So there are 2 out of 12 chances that the month starts with the letter A. So 1 minus 2 over 12 is 10 over 12, which actually reduces down to 5 over 6. There's a 5 out of 6 chance that a month does not start with the letter A. And that's how you do complements. I kind of want to show you another one. This is a tough one because it's dealing with prime numbers. It says if the spinner to the left is spun, find the probability that it lands on a number that is not prime. Again, the reason this is a good one to go over is, do you remember what prime means? Because see, we're going to subtract all the ones that are prime from 1 to find how many are not prime. So all I got to do is just go through here real quick and figure out, well, what's prime? Well, remember, prime is that it can only be divided by itself in 1. So 1 is prime, and believe it or not, 2 is prime as well, because seriously, it can only be divided by itself in 1. 3 is prime, right? 4 is not. It can be divided by 1 and 2 and 4. So not prime. 5 is prime. 6, not prime. 7, prime. 8, not prime. 9's not. 9, 3, 1. 10's not prime. 11 is. 12's not. 13 is. 14's not. 7, right? 15's not. 3 and 5 and 1 and 15. And 16's not either. So how many are actually prime? How many did I highlight? 1, 2, 3, 4, 5, 6, 7. So 7 out of the total 16 are prime. So how many are not prime? Well, subtract. 1 minus 7 over 16 is, let's see, what is that? It's going to reduce, I think, so that's, let's see, 16 minus 7, that's 9 out of 16. And let me think, will that reduce? I don't think so. So the chance of it happening, landing on something that is not prime is 9 out of 16. Now, just to go back and check, go count the ones that we didn't highlight. 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom. We got it right. No problem. So there it is. Okay, that's the idea of complements. It's when you're trying to use the ones that the probability that it will happening and subtracting that from 1 to find the probability that it will not happen. Okay? Okay, now compound events. Compound events are a little different. Because as you see in the little note over here to the left, compound events is when you have the probability of 2 or more simple events occurring. Okay, 2 or more. So here's the deal. It's got a little trick to it. If you notice up here at the top, there are 2 types. Okay, there are independent and there are dependent. So what we have to do is we kind of have to decipher when you're doing multiple events. You got to decipher which one is it fitting under. Is it independent from one another or is it dependent? So if you look at the instructions, here's what it says. When the outcome of one event does not affect the outcome of the other event. Well, when that happens and you're finding the probability of multiple events happening, you're going to take the probability of one of them happening and you're going to multiply that by the probability of the other one happening. And that's it. That's how you come up with the answer. Very straightforward. And a lot of times we start thinking, well, how could dependent events be done? Well, here's the thing. The outcome of one event does affect the outcome of another event. Okay, so here's the point here. If I had the probability of A, then you multiply that by the probability of B after A occurs. After A occurs. So I want to show you guys, or just briefly tell you a quick explanation of this, okay? Here's kind of an explanation of the difference, okay? If I said that I was going to divide this classroom out between guys and girls, and I were to say that I'm picking one guy and I'm picking one girl, and I said, hey, what's the probability of that one girl and that one guy being a certain person? Well, that would be completely independent, right? Because since those categories are different, I'm not going to pick one that could affect what I'm going to pick with the other, right? Okay, so what about dependent events? Well, here's the difference there. What if I said that I'm just going to take this whole class of students and I'm going to pick 2 students? What's the probability that it's these 2 people? Well, that one's a little different because if I'm just basing it on the whole class, if I pick this first person, can I pick that person again? No, they're already picked, right? Well, if they're already picked, does that change the probability of the next person? Of course it does, because that person is gone, because that person affected my next possible choice there. You see the difference? Independent versus dependent. And you're going to be able to see this if you read carefully. And I know one of the reasons why people don't love probability is because you do have to read. But if you pay close attention and you understand what you're dealing with, then you're going to have no problems with this whatsoever. Okay, so let's check this out so I can explain to you the difference between independent versus dependent. A die is rolled 3 times. Standard dice rolled 3 times. What's the probability of getting ones on each roll? See, we're having 3 things happen this time. If there's 3 things happening, you have to have 1, 2, 3 events, and you're multiplying all of those events. That's how it works, okay? So what is the probability that I'm going to get a 1 all 3 times? Okay, now that's crazy, right? And you're going to see the probability and understand hopefully a little better what makes that so crazy. So first, only focus on the first roll. What's the chance of me getting a 1 on just the first row? Well, it's 1 out of 6, right? Because there's only 1 1 on the dice, and there's 6 total numbers on the dice. So the chance of getting a 1 in that first dice is 1 out of 6. Now here's my question to you guys. When I pick up that dice to roll it again, is that 1 gone? Of course it's not gone. The 1 is still there, and if I roll the dice again, there's a chance I would get a 1, right? It didn't matter that I got 1 the first time. It could happen the second time too. So once again, it would be a 1 out of 6 chance. And the third time as well, a 1 out of 6 chance of rolling one. So what's the probability of getting ones all 3 times? And this is where things get crazy. If you multiply 1 over 6 by 1 over 6 by 1 over 6, and I encourage you guys to do this in your calculator. You could also do 1 over 6 raised to the third power. But when you do that, your answer is going to be a 1 out of 216 chance. Think about that. You could roll dice all day long in groups of 3. You would have a 1 out of 216 chance of rolling 3 ones in a row. That's crazy. And again, that's why gambling can be very, very dangerous, because the chance of winning is very, very difficult. Okay, so let's look at the next one. And there you see what we called a dependent or an independent event. The first roll had no effect whatsoever on the second roll. Okay, so number 12. A coin is tossed, then a day of the week is selected. What is the probability of getting tails and then a day starting with the letter T? Once again, these things are completely independent of each other, right? You have how many events happening? 2, right? You're picking it, you're getting either heads or tails. You're getting tails, and then you're picking a letter that starts with the letter T. So we're only dealing with 2 events, and they are completely independent of each other. The coin has nothing to do with the day of the week. So first of all, that coin, what's the chance of getting tails? Well, there's only 2 sides to a coin, right? And one side is tails. So 1 out of 2 chance. And then when it comes to the letter of the week, or letter of the day that starts with a T, what are they? Well, there's 7 total, right? So you got Monday, Tuesday, there's 1. Wednesday, Thursday, that's 2. Friday, Saturday, Sunday. So there's only 2 out of 7 chances of doing that. So what's the probability of both of those occurring? Well, multiply straight across. 1 times 2, 2. 2 times 7, 14, and that reduces to 1 over 7. Now, if you just type that into your calculator and let the multiplication do its own thing, it would have simplified it for you down to 1 over 7. But anyways, that's how you do independent events. Let me show you a couple that would possibly include dependent events, okay? Let me go to, for example, number 15. I'm going to go a little backwards here. See, 15 and 16 are way different than 13 and 14. You see, with 13 and 14, they want you to tell the probability of getting purple and then yellow. So again, these are kind of, these could be dependent, but they're not, because if you read the instructions, it says the bag contains 8 red, 14 purple, 6 yellow, and 4 green. A crayon is selected, and then this is a really important word. It's replaced. So it's like you pulled it out, you looked at what it was, and then you tossed it back in the hat. You see, if it's replaced, then it's not going to affect the next possible crayon that you pull out. If it's not replaced, it does. Well, these are replaced, but I still want you to see the difference between 13 and 15. Okay, look at 13. Actually, I'm wrong. 15 is also independent because of the concept of replacing. Let me explain. 13. What's the probability of a purple, then yellow? So the first thing I want you guys to consider is how many different crayons am I pulling out? Purple, then yellow. That's 2. So we have 2 events, right? What's the first event? Well, the fact that the crayon is purple, right? How many purple ones are there? 14. And then how many total crayons are there? Did y'all tally those up yet? 8 plus 14 is 22. 22 plus 6 is 28. 28 plus 4 is 32. So there's 32 total crayons. All right, now what's the second event? Well, remember, you're replacing that crayon. So let's just say you happen to get lucky and you pulled out a purple one. You're putting that purple crayon back into the hat. What's now the chance that you get a yellow one? Well, there's 6 yellow out of the total. And again, there's still 32 crayons in the hat because you put the other one back. So you got 14 out of 32 times 6 out of 32. So type that in your calculator. Let it simplify it for you. That's a 21 out of 256 chance. Divide that, change it to a percentage. That's what I like to do sometimes, so you can kind of really see, what the real percentages are. Because when we see them as fractions, unless they're fractions we're really familiar with, like 1/2 or 1/4 or something like that, we don't really know what they are, what those percentages are. So I want you to look at number 15, and then we're going to go to some that are more like what I was telling you earlier. They're dependent, okay? But these are independent because those crayons are being replaced. So what's the probability that you're having two purples? Again, two events, two fractions, and we're multiplying. Well, what's the first one? Purple. Well, there's 14, again, out of 32. You're replacing it. You're putting it back in the hat. So don't you still have the same chance to pull another purple? Absolutely. So it's 14 over 32 times 14 over 32, which if you type it in your calculator and let it reduce, that's 49 over 256 chances. Okay? That looks like about a 20% chance if you type that in your calculator. It's about 18 or 19%. Okay, now here's the difference. These are my dependent events. Well, why? Why are they dependent? Because this instruction says that you pull the crayon out and then it is not replaced. You don't put it back in the hat. Well, why is that dependent? Because when I pull something out, it's gone. It's gone. It's not still in the hat. So when I reach back into the hat, it's going to change my fraction because that crayon is no longer there. It's no longer available. So let me show you these. Let's jump over here to number 18. I'm going to go left side, right side. So 18. Again, what are my number of events? Well, it's the probability of purple, then green. So two events, so two fractions that we're multiplying. So what's the probability I pull a purple? Well, we just did that a bunch, right? Purple is 14 out of 32. Now listen, that purple crayon does not go back into the hat. So how does that matter? The next one I'm picking is green. Well, here's how it matters. How many crayons did you start with? 32. But that purple crayon does not go back in there. So why did it affect the next one? Because there's no longer 32 crayons. In the hat, there's only 31. Now, how many of them are green? Well, up top we see that there were a total of 4 green crayons. So my two fractions that I'm multiplying are 14 out of 32 times 4 over 31, because you just pulled that out and it's gone. So it's not a total of 32 anymore. So when you multiply that using your calculator, you get a 7 out of 124 chance. That's less than 10%, okay? Now here's where it gets really interesting. What about when you do something like number 20? What's the probability of getting two greens? Again, that's two events that you're going to have two fractions multiplying to each other. But with my first one, what's the probability of it being a green? Well, remember there were 4, right? Out of 32. But here's why this one's different. You don't replace that green one that you just got lucky. So you had a 4 out of 32 chance. Let's just say the one you grabbed it was green. You don't replace it. That green one is no longer there. So not only does the bottom number change by going down 1, but now how many green ones are still left in the hat if that 1 is gone? Well, there's only 3 left. So not only does the denominator drop, because it's the same color crayon, the top number drops as well. So it's 4 over 32 times 3 over 31. And of course, when you multiply that with your calculator, you're going to get 3 over 248. And the chance of that, man, is almost slim to none. I mean, divide that. 3 divided by 248, you're talking about almost less than 1%. No, not less than, just above 1%. So very, very unlikely that that would occur. All right. So let me show you one more. Let's go to number 21 over here, again, with a deck of cards. Now that you know a little bit, hopefully, more about a deck of cards, here's what it says. A card is drawn from a standard deck, not replaced. Very, very important word, not replaced. So is that independent or dependent? Definitely dependent. And another is drawn. So you draw a card, you don't replace it, and then you draw another card. So how many events are occurring here? Hopefully you just said 2. So we have 2 fractions, we're multiplying them because we want to know the probability of those both happening, okay? So first, what's the probability of choosing a heart? Well, remember how many hearts I said there are in a deck? There's 13. Out of how many? 52. So 13 out of 52 chances. All right, so what's my next one? Well, it's what's the probability of pulling out a spade? Well, once again, did the fact that I just happened to grab a heart affect how many spades are still left there? No, there's still 13. However, is that original heart still in the bag or the hat? No. So there's not 52 cards anymore. There's only 51. So dependent event, you multiply these, that's 13 out of 204. Okay, very slim chance. So one more time, let me just take you real quickly through what we talked about. Theoretical probability is a fraction. Favorable events on top over total number. You can have single events where you just have a single fraction, and you are able to see that based on the reading. Now, number 4 was a little tricky, but the rest of them I think made a lot of sense. Then we talked about complement of events, where in some cases it's better to tell or find the probability of something not happening by simply subtracting the probability that it happens. That's what complements were. Compound events are when you have multiple things happening, you're going to have that many fractions being multiplied. Okay, if it's 2 events, you'll have 2 fractions. If it's 3 events, you'll have 3 fractions, so on and so forth. If the first one does not affect the second one, you just multiply your probabilities. But if the first one does affect the second one or the third one, whatever, those dependent events, you have to change your fractions based on whether or not that card, that day of the week, that marble, whatever it might be, that crayon is not there anymore. So the key words that we're going to look at is whether it says the word replaced or not replaced. That's the big key. Replaced means it's independent. Not replaced means it's dependent. So pay close attention to those in your homework. Speaking of which, Ms. Higdon has either given you or will give you your homework assignment. It is this worksheet, Theoretical Probability, and it is numbers 2 through 26 even. I know it says it's homework number 2, but it's the first one we're going to do. We didn't do the first. We're not going to need the first lesson. So all of those highlighted ones, 2 through 26 even. I want you guys to give this your best effort. We'll talk about it tomorrow, and we will move on. Okay, I'm not going to reteach this. You're hearing me teach it now. You've got Ms. Higdon who can maybe help explain anything that you didn't understand. But again, please do your homework 2 through 26 even, and I will see you tomorrow. Have a great day.